last time. So we started dealing with sigma notation en route to understanding area. So sigma notation, you remember this sigma as k goes from 1 to n, let's say, okay, 1 to n of k. Remember what this was? This means you add up 1 plus when k equals 1, you have a 1. When k equals 2, you have a 2. And you add all these things up until you get to n. And we saw that this was Janine, n times n plus 1 over 2. Beautiful. So what if we had something like 13 plus 19 plus 25 plus 31 plus 6001? How would you do something? How would you figure out something like this very, very easily? What are these numbers? Is this a pattern? Is there some pattern to these numbers? What am I skipping by here? I'm skipping by 6, skipping by 6, skipping by 6, okay? And these are all one more than a multiple of 6. So 12 is a multiple of 6, 13 is one more, 18 is a multiple of 6, 19 is one more. That's how I knew I could stop at one more than 6,000, right? How would you add all of these up? Well, we can try the same strategy. If I say S, let S be this sum, I can write S again as the same sum but backwards, 6001 plus 5995 plus and so on down to 13. If I add these two sides, on here, on this side, I get 2s. Here I get 6014. And I get another 6014, and I get another 6014, all the way down to the last 6014, right? Why are the sums all the same? Every time I move over, I go up by 6. Every time I move back, I go down by 6. So this goes down by 6, this goes up by 6. That's why the sums are the same. Does that make sense? And so the only question is, how many terms are there? So this is 6014 times something, and the something is how many terms there are in this sequence. Now, I don't know about you, I find this very difficult and tedious to figure out. So here's a trick I taught my kids. So you start with you just write the sequence 13, 19, 25, ... 6001. Okay, you're skipping by 6s. You add 6 to get from one sequence to the other. So let's do something. Let's subtract by something that makes the first number equal to the step size. You'll see why I'm doing that in a second. So what do I have to subtract from 13 to get to 6? 7. So I'm going to subtract 7 from every term. 19 minus 7, 12. 25 minus 7, 18. You see, now we're seeing the multiple of 6. Oh, that's much more convenient to think about the multiples of 6. But now I know what to do with this number. I have to subtract 7. 5994. Okay, once we've done that, we know that these are all multiples of 6, so we can divide by 6. Divide by 6. 6 divided by 6, 1, 2, 3. Okay, this 6,000 divided by 6 is 1,000, and I have one fewer 6. So this is 999. Does everybody see that? But now I know exactly how many terms there are in the sequence. This is the first term, this is the second term, this is the third term, and this is the 999th term. Cool? Like that trick? So keep that in mind. So that's exactly what goes here, 999. Does that make sense? And that's twice s. That means s itself is well, half of this number. So let's just leave it as 999 times 3007. Everybody see how I got that? Is anybody lost? Okay, never mind. Thank you. How did I get half? Because this is 2s. I added s to itself in order to have this 6014. And then the question was, how many times do we have the 6014? That we answered with this little trick, so we get 999. But that's twice s, so I need to have it to get back to what s is. What s adds up. Here's a good exercise. Can we do the same thing with sigma notation? So what is this very s, same s? Can we write it with sigma notation? So it's the sum, let's say, as k goes from, I guess we start one more than so 12 is a multiple of 6. So let's start with k equals 2. And this will be 6k plus 1. Do you see why I did that? If I'm looking at one more than multiples of 6, that means I take an integer, I multiply it by 6, and I add 1 to it. Okay, so when k is equal to 2, 2 times 6 is 12 plus 1 is 13. That's the first term. And how about the last term? Well, it's 6,000 plus 1. So k should end at 1,000. You see that? Okay, so that's one way you could have written it. That's a perfectly fine sigma notation for this sequence. You could have also said, no, I want k to start from 1. So if k starts from 1, then, okay, I'm still skipping by 6, but now I start not by adding 1 to every term. But if k is 1, then I start with 6 plus what? Plus 7. 6 plus 7, 6k plus 7 is what will get me that first term of 13. When k is equal to 2, I get 12 plus 7, that's 19, that's my second term, and so on. Everybody see that? And what's the last term? 999. So in effect, all I've done is I've changed k from running from 2 to 1,000 to running from 1 to 999. And now you can really clearly see what we're doing when we do this operation. We're skipping by 6. So we subtract 7. Now we just have a sum of 6k instead of 6k plus 7. Then we divide by 6. So now we just have a sum of k from 1 to 999. Okay, and that's exactly what gets us this formula. By the way, now we can use the things that we know about sigma notation. So this is a sum of all of these things, but sigma notation is linear, right? If I have a constant, so I add this constant 7. How many times do I add the constant 7? 999 times, so times 999. Plus, there's a factor of 6 that's being multiplied by everybody, so I can pull that 6 outside. 6 times the sum of k, well, let me leave it, the sum of k as k goes from 1 to 999. Does everybody see how I'm manipulating these things? We got to get really good at this. This is the next thing we got to get good at. Sigma notation, moving things around, being flexible with terms like this. But what is this? Exactly. It's the formula that, yep. That's what Dan's saying, what Jenny told us. It's 999 times 1,000 over 2. N times n plus 1 over 2, where n is 999. Does that make sense? So look at what we get here. 6 over 2 is 3 times 1,000 is 3,000. That's 3,999s and 7 more 999s. That's 3,007. That's the same 3,007 999s that we saw from the other point of view. Okay, does this make sense? Can you guys do this when you see this on your homework, on your exams? Yeah, you can manipulate these things. Ask me, because if you're confused, I guarantee you other people are confused. One. Right. So the first thing is that if I'm adding 6k as k goes from 1 to 99, and I add 7 as k goes from 1 to 99, that's this. So I can break this as a sum of 6k plus a sum of just the number 7 as k goes from 1 to 999. As k goes from 1 to 999. Does that make sense? Yeah. So then I'm adding that 7 to itself 999 times. So that this term is this. And then I have 6, but the 6 I can pull out. Does that make sense? Other questions? Where's the k in here?
Oh,
when I switch to numbers here?
Yeah.
Right there. Where's this come from?
Yeah, where you scroll up and show the formula.
Ah, you want to see the formula again. The formula is if you add up the first n numbers, the answer is n times n plus 1 over 2. That's what we proved last time. And so I'm doing exactly that. I'm summing the first n numbers, but n is 999. So it's 999 times 999 plus 1 over 2. Yeah.
If you use it from k equals 2, would you do 1,000 plus 2?
Yeah, beautiful. Let's do k equals 2. Let's figure it out from this. If you had done it like this, what would you get? Should we make this the quiz? No, it's too simple for the quiz. Let's do it all together. You're adding 1 to itself how many times? 1,000, except you're not doing the first time. So you're adding 1 to itself 999 times. Okay. And then you have 6 times the sum of k from 2 to 1,000. Well, that's the sum of k from 1 to 1,000, except you're forgetting the first term. What's the sum? So let's sum of k as k goes from 1 to 1,000, but I'm forgetting the first term. So the first term would be k equals 1. Does everybody see that? Everybody see how I got that? Okay, for this we have a formula. We know what this is. And Annabelle? Where n is 1,000, so 1,000 times 1,001 over 2, right? N times n plus 1 over 2, and then we're going to subtract 1 from that. And okay, so this is, gosh, how do you want to do this? Where are we going to get a 999 here? It's going to be the fact that we're subtracting 1. Yes? Very good question. Very good question. This is a place where PEMDAS is not well established. So when I write something like this, usually I mean this whole thing is getting added up. Really, I should have parentheses around this just to make sure that you know that that's what I mean. For exactly the reason that you said, because here I'm not adding up k minus 1 from here to here. I'm adding k from 1 to 1,000. And then I'm subtracting 1 afterwards because there was no first term. It started at k equals 2. So a good habit to get into is just to always put the parentheses in sigma notation. I'm going to try to do that for exactly the reason that this is a place where you usually write such things and you'll see such things in your book without parentheses. But then if I mean, no, sum the first k numbers, and then after you're done summing that, subtract 1 once, not subtract 1 every time. So that's the yeah, let's use parentheses. Great question. Great question. So everybody see that point? What that was about? Okay. Dan.
And so start from k equals 2, just back to.
You mean if I started from k equals 3?
Yeah.
So if we started from k equals 3, we'd have to subtract off the first term and the second term. So I'd subtract off 1 and I'd subtract off 2. So anyway, this will again come out to, I'll let you check the math for yourself, to 999 times, what was it, 3007 or something. Let's do exactly what Dan said. What if I sum k goes from 5 to 1,000 of k? Well, isn't that the sum as k goes from 1 to 1,000 of k, which we know the formula for, minus, let's make this even harder, 500 to 1,000. Minus the sum, yeah, so let's put parentheses so that it's clear what the minus applies to and what the sigma applies to, minus the sum as k goes from 1 to 499. Yeah, because the 500th term is included. The way sigma notation works, it's not very, it's just, it's the standard. You start at this number and you end at this number. So it's not like, oh, it's closed on both sides. So we do want the 500th term. We don't want the 499th term or the first term or anything in between. So minus this. Does that make sense? And so that you apply the formula to both instances. So here you'll get 1,000 times 1,001 divided by 2 minus 4,999 times 500 over 2. Does that make sense? And if it's just a couple of terms, don't bother using the formula. If it was only 3, then you subtract off 1 and you subtract off 2. Okay, are we getting the hang of this kind of thing? All right. What is 1 plus 4 plus 9 plus 16 plus up to 625? Maybe this should be the quiz. No, but no, it's not the quiz. But okay, it's not the quiz, but can you solve it anyway? Can you solve it on your own? How would you do it? Can you sum this? Hater. Okay. You don't want to start at 1? Okay. Okay. It's not skipping by 4. This is skipping by 3. This is skipping by 5. This is skipping by 7. These are the squares. 1, 4, 9, 16, 25, 36. So that's a good, I see why you wanted to start at 0, but it's not an arithmetic progression now. It's a polynomial progression. It's the sum of the squares. As, yeah, what's the square root of 625? 25, as k goes from 1 to 25. If I give you 25 quarters, you guys don't play video games anymore. I used to come home from school and grab a stack of quarters and ride to Al John's Pizza down the road, and the quarters would be shaking in my pants as I bike. Every time you pedal, you just hear all the quarters, and you can play like Street Fighter 2 for the next 6 hours. So everybody who grew up with me knew exactly how much 25 quarters bought you. 25 quarters is $6 and a quarter. It's 24 quarters is $6. So anyway, all right. So 25 times 25 is 620. That's just a number I'm going to know for the rest of my life. Anyway, do you remember we discussed a formula for the sum of the first something squares? Well, yes. So let me record that formula over here. A sum as k goes from 1 to n of k squared was n times n plus 1 times 2n plus 1 over 6. So in the case of n equals 25, I get 25 times 26 times Peter.
Since like for like the k, since it's like 2 terms or 2 equations, it's over 2. S this is 3 times that by 3, 2 is what it says.
You can have all kinds of mnemonic for these things. I have a feeling you're going to use these formulas so much over the next 2 weeks that it'll just be part of you. Like, how are you going to remember that 3 times 7 is 21? I don't know. You just do it so much that you don't even think about it. So I don't know how I have this formula memorized. I don't have like it's just something that I know because I need it all the time. So where were we? N is 25, n plus 1 is 26, 2n is 50, plus 1 is 51, and I'm dividing all that by 6. Why is that even going to come out to a whole number? Is this thing divisible by 6? I'm adding whole numbers. I better get a whole number. 26 is divisible by 2. Who is? 51 is divisible by 3. So yes, this will be a whole number. Okay, and that's a general fact. So whatever that is, we don't have to, you want to work it out? Let's see. No, we don't need to work it out. Well, it's not hard to work it out. 25, if I divide this by 2, I get 13. And if I divide this by 3, I get 17. All right, that I'm definitely not going to work out. Okay, so the point is it's a whole number. Okay, we know how to add squares. We know how to add cubes. 1 plus 8 plus 27 plus 64 plus 125 plus, what do I know is a cube? I know what 100 cubed is. It's easy to cube 100. That's the only other cube I think I know. So if I added all the cubes from 1 to 100, what would it be? So let me show you this. This is kind of fun. Okay. So we want a formula for the sum of k cubed as k goes from 1 to n. Okay. So this is a 1 by 1 square, and there's only one of them. So there's 1 by 1 square. Let's just call that 1 squared. Here is a 2 by 2 square. And here's half of a 2 by 2 square and another half of a 2 by 2 square. So that's 1 2 by 2 square and one more 2 by 2 square. So that's 2 2 by 2 squares. Everybody see that? Here's a 1 2 3 by 1 2 3 square. and a 1, 2, 3 by 1, 2, 3 square, and 1, 2, 3 by 1, 2, 3. And there are 3 squares. Each of the squares is 3 by 3. I'm computing the area of this shape. Everybody see that? How does it continue? 1, 2, 3, 4. 1, 2, 3, 4. So here's 4 by 4. This is 4 by 4. Here's 1, 2, 3, 4 by 4. Here's another 4 by 4. 1, 2, 3, 4 by 4. This is another 4 by 4. And now I got a 2 by 4. This is 2 by 4 and another 2 by 4. So I have how many 4 by 4s? 1, 2, 3, and 2 halves of a 4 by 4. So that's 4 4 by 4s. And then I have a 5 by 5. 1, 2, 3, 4, 5 by 5. Here's 5 there. And this is 1, 2, 3, 4, 5. Ah, come on. So that's 3 5 by 5s. And here's 2 more 5 by 5s. So that's 5 5 by 5s. Everybody see that? That's the total area, but there's another way to compute this area. This is 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2 plus 3 plus 4 plus 5 by 1 plus 2 plus 3 plus 4 plus 5. So this whole area, if you compute using the squares, you get this. If you compute just using the lengths, you get 1 plus 2 plus 3 plus 5 squared. Everybody see that? Does that make sense? And so the sum of the first k cubes is the sum of the first k numbers, the sum of the first k numbers as k goes from 1 to n squared. And we know what the sum of the first k numbers is. It's n times n plus 1 over 2. So this is n squared times n plus 1 squared over 4. So this whole thing, this is the sum as k of k cubed as k goes from 1 to 100, because this is the 100 cubed, 100 from 1 to 100. That will be, by this formula, 100 squared times 101 squared over 4. Cool? Okay. Everybody, that makes sense? You don't need to know these proofs. I'm just reminding you what kinds of things I want you to have facility with, mastery. I want you to have mastery of these kinds of manipulations. So we've learned that the sum of k as k goes from 1 to n is n times n plus 1 over 2. I'm just recapping. The sum of the squares as k goes from 1 to n is n times n plus 1 times 2n plus 1 over 6. And can I fit this here? Let me just write it below. And the sum of k cubed as k goes from 1 to n is what we said there. It's this quantity squared. N squared, n plus 1 squared over 2 squared. Okay, so these are three identities that we really are going to need for what we're doing going forward. All right, how do we get on this topic? We're trying to understand area. So last time we were looking at area under meaning between the function and the x-axis. What was our function? 1 plus x squared. Area under the function 1 plus x squared. So here's 1 plus x squared. And we were looking at this from x equals 1 to 2. So here's 1 and here's 2. At 1, the value of the function is 2. At 2, the value of the function is 5. Okay, we're going to try to figure out this area. So this is the area that we're interested in. So under means between the graph of y equals f of x and the x-axis, including if the graph dips below the x-axis, that's negative area, right? So the area is signed. Okay, and what we said is that the area is bounded. Did we do an upper sum or a lower sum? I think we were doing the upper sum. The area is no more than if we break it up into a bunch of rectangles, and the rectangles are always above the curve. So they're bigger. So let's just keep the calculation going. An upper sum. Okay, so the area is always at most. Now, first we divide it into 2 pieces or 4 pieces or whatever it was, but we can divide it into any number of pieces. So let's say we divide into n pieces. Divide into n equal pieces into n pieces. So the width of each of these little intervals is 1 over n. The total width is 1. So there's n pieces. So each width is 1 over n. So the area is at most, let's use sigma notation. We're going to sum a bunch of little rectangles. We're going to sum a bunch of little rectangles. As k goes from 1 to n, there's going to be n rectangles. The width of each rectangle is 1 over n. And the height of each rectangle, if we're looking, so what is the kth point here? So we're keep skipping by 1 over n. So we start at 1, and then the kth point, the kth location, let's call this, I don't know, xk, x sub k. Okay, so x sub k, right? This is x1, x2, x3, up to x 1,000 if n is 1,000, whatever. So the kth location is 1 plus 1 over n times k, right? We've shifted over k times. Have I lost anyone? This is a review of what we were covering last time. Make sense? So far, so good. How many are with me? Okay, good. Okay, so what's the height of each of these rectangles? It's just, yeah, it's f. Yeah, you're plugging in the value of the function. Let's just remember first that it's just the function, and that it's the function at 1 plus k over n. So far, so good. As Dan said, we know what the function is. So this is equal to a sum as k goes from 1 to n, 1 over n, which, by the way, is a constant, doesn't depend on n, and it's multiplying everything. So I could have pulled it outside, but never mind. Bug. The function takes whatever your input is and takes 1 plus the value of that input squared. Everybody happy with that? So what does the function do to x? It squares x and adds 1 to it. This is the location. This is the height of each rectangle. The height of the kth rectangle is the function value at 1 plus. So look at when k is equal to 1, I have 1 plus 1 over n. That's this endpoint. When k is equal to 2, I get 1 plus 2 over n. That's this endpoint. When k is 3, I get 1 plus 3 over n. That's that endpoint. And when k is n, I get 1 plus n over n, which is 2. That's this last rectangle. Okay, does that make sense? And so, great. So now we have an expression for the area, and this is an upper bound for the area. So let's continue the calculation. We can simplify the algebra on this. We did this last time. We get a 1 squared plus another 1, that's a 2, plus 2, yeah, exactly, 2k over n. There are 2 intermediate terms, and then the last term squared, k squared over n squared. Okay, and all of that is being multiplied by 1 over n. So if I take the whole thing, I multiply by 1 over n, I multiply by 1 over n, and I multiply by 1 over n. And I want to sum this as k goes from 1 to n. Who's with me? If you didn't raise your hand, can you tell me where you're confused? Same. Okay, so that was the function. So here I have 1 over n, which is the width of my rectangle, and then f of 1 plus k over n. Are you happy with that bit of it? Okay, so then what does f do to any input? F takes that input, squares it, and adds 1. So I took this input, I squared it, and then I added 1 to that. Does that make sense? That's just what F is. That's the F that we chose last time to whose area we're gonna. Yep. Other questions? Okay. All right. Jenny, you didn't tell me I needed to put parentheses here. I don't, because you see, the reason you don't have to put the parentheses here is because if you think of the parentheses as being here, K doesn't make sense by itself. K is just floating out in space. It's only when you sum on K from 1 to n that if you see a K, it must be that it's getting summed. So that's why people don't put the parentheses, but I think one should. I don't know. I don't know what the pedagogy on this is. All right. So we're going to add 2 over n. How many times are we going to add 2 over n? Yeah, it's just a constant. We're going to add it n times. So that's 2 over n times n. Then I have this factor of 2 over n squared. 2 over n squared is not does not depend on k, does not change as k changes. And then I have a sum of k as k goes from 1 to n. You see why these formulas are going to come very much in handy in a second. And then I have this other constant, n cubed. So the sum stops here. And then I have another constant, n cubed. And then I have to sum as k goes from 1 to n, k squared. Oh, if only we had identities for the sums of k and the sum of k squared. Let me just simplify this a little bit. 2n over n is 2. Here I have a 2 over n squared times altogether n times n plus 1. But what happened to the energy? You guys are asleep? Hater, it's no good. You okay? All right. You'll be my thermostat, all right? If it's too, like, if everyone, I don't know, needs to run around for a second or something, you'll let me know. All right, what's the sum of k squared? Peter?
N times parentheses n.
All over. See, you can remember it. You see why you needed these things. All right, so whatever the value of n is, the area under that curve is always bounded above by this quantity. And as you might imagine, the larger you take n, the less overhang, the less you're overestimating the area. So what might be a reasonable thing to do? Let's take the limit. This is true for any n. This inequality is true for any n, true for any value of n. So we may as well take the limit. So where does this expression go? Where does this expression go as what is the limit of this as n goes to infinity? If only we had studied the asymptotic at infinity behavior of polynomials or rational functions. We know exactly what to do, right? So there's a 2. There's a 2 over 2. And the leading term here is n squared. On the bottom, the leading term is, so this is just 1. And this is 2n cubed on top and a 6n cubed on bottom, which has a limiting value of 1/3. Yeah, or 3 1/3, yeah, 10/3, whatever. 3.33, 3 1/3. Of course, when you write this, it's not 3 times 1/3, it's 3 plus 1/3. So PEMDAS is all over the place. Anyway, does that make sense? Should we see this in action? Of that thing is a function of capital N. See, the area doesn't depend on n at all. And we made up this number n. We said we're going to break it up into 10 rectangles, or 100 rectangles, or 1,000,000 rectangles. And we gave an upper bound for the area. But the area is whatever it is. The area doesn't care about how many rectangles we chose to break it up into. So this inequality is true regardless of the value of n. And it gives an upper bound for the area. So we can do whatever we want with this function of n, and that'll still be an upper bound for the area. That is the limit of this function as a function of n. Yeah. So this function here, this you can think of as a function of n. Let's call this s upper of n or something. And then what this limit, and so the limit as capital N goes to infinity of this s upper of n is this number 1/3. Does that make sense, Alyssa? We should figure out a lower limit, because this by itself doesn't tell us what the area is, just tells us an upper bound. It's going to be the same. It doesn't necessarily have to be that for continuous functions, it will be actually.
N minus 1 for all n.
That's exactly one thing that we could do. We could take this area and we could say, so a lower bound. Okay, so let's do it. Let me grab this picture and we can move it down below. So we gave an upper bound. Now let's give a lower bound. But this we can do much more quickly or efficiently or something. So now, instead of taking the endpoint, the right endpoint, which will give us an upper bound, let's take the left endpoint. That'll give us the lower bound. What's the left endpoint? It's just replacing k by k minus 1. So that instead of starting by shifting by 1/n, instead of evaluating the first term at 1 plus 1/n here, this first height, we're going to evaluate the first height just at 1 plus 0/n. And then we go up to n. Raga. We absolutely can just do k/n. So Raghav is saying, instead of doing that, that's going to make our algebra a little bit messier. Just start from 0 and go up to n minus 1. Great. Let's do it like that, if you prefer. It's the same thing. I think this algebra will be a little bit cleaner, because we've already done this algebra. So now I can go up and copy the algebra, because this part is the same. The only thing that's different is the range of k's. Okay, so the algebra is the same, which means I can grab this much of the algebra. So this is a lower bound. I'm going to grab this much of the algebra, and all I have to do is change the endpoints from 0 to n minus 1. Maybe I do prefer this to Blackboard. I don't know. I'm sorry, you didn't hear that. I love Blackboard. All right. Kth position, is that what's supposed to be here? Position. Okay, so here's this sum. Now we can work out what the sum is. So I have 2/n. How many times do I get it? N times. So that's 2/n times n. There's this factor 2/n squared, and I'm summing k as k goes from 0 to n minus 1. The beauty is when k is equal to 0, I'm not adding anything. I'm adding 0. So this is the same thing as summing from 1 to n minus 1. But I know a formula for summing the 1 to anything. In particular, I can apply that formula to n replaced by n minus 1. So what do I get? Times n minus 1 plus 1 all over 2. Does everybody see that? So this term turns into that term. How many follow what I'm doing? Okay, not everybody. So all I said is there's this factor 2/n squared that we had pulled out. And we were left, let's do it, I'm doing too many steps at once. We were left with a sum of k as k goes from 0 to n minus 1. Okay, and let's leave it like that for a second. 1/n cubed, and here I have a sum of k squared as k goes from 0 to n minus 1. So this is the line above the line that I copied. Or below, whatever. If I look at the k equals 0 term, that means add 0. So it doesn't do anything if I say, well, don't bother adding 0. Nothing happens at 0. 0 squared is also 0. So nothing happens at 0. I may as well start at 1. And the sum, so here I get 2 again. I have a factor 2/n squared. The sum of k as k goes from 1 to anything is anything times anything plus 1 divided by 2. So that's anything times 1 more than anything over 2. That's this sum. And finally, I have my 1 over n cubed term. And the sum of k squared, Peter, can I pick on you again if you don't mind?
This n times n plus 1 n up to n plus 1 over 7.
See, you got it. But what is n? It's not n anymore. We only go up to n minus 1. So we go up to n minus 1, and then n minus 1 plus 1, and then 2 n minus 1 plus 1 over 6. And every value of n gives a lower bound for the area, regardless of what the value of n is. We're losing some of the area because we keep taking rectangles that are smaller than the true area. But the more and more rectangles we take, the less we lose. The closer this becomes to the true area, or so we think. But anyway, for any value of n, this is a lower bound. So if I take the limit, so this we can call the lower sums. And let's take the limit of these lower sums as n goes to infinity. So let's see, I have a 2, that's just a constant. Leading coefficient, leading term is n squared on top, n squared on bottom. 2 over 2 gives me a 1. And here, even though we replaced n by n plus 1, that's lower order. So we still get 2n cubed on top and a 6n cubed on bottom for a lower bound of 3 1/3, exactly as they are upper bound. So the area has no other choice. Damn. Just because our formula was from 1 to n minus 1. There was no reason to do it. Just so it looked like the formula that we're used to. Does that make sense? Should we see this in action? I think we can actually do this. Let's see this in action. Okay, so what's our, let me get an A and a B starting values. Oh, come on. Add a slider for A, add a slider for B. Okay, I'm learning Desmos. This is actually a pretty cool thing. What's our function? F of x is 1 plus x squared. Okay, that's 1 plus x squared. Now I want to restrict this. I want to restrict this to A to x being between A and B. And B we're going to set to 2. Okay, so here's our function. Maybe it's nice to see the whole thing. Let's see the whole thing, but then let's graph y equals f of x on a restricted range. Okay, so the blue is what we're going to actually compute the area under. Okay, then we're going to take some value of capital N. Add a slider for capital N. Okay, so capital N will go from, I don't know, 1 to 1,000, 100, stepping by 1. Capital N is an integer. And then we're going to take a typical value of k. So k will be our index. Will run from 1 to capital N. 1 to 100, 1 to 1,000, whatever capital N is. Okay? I didn't know you could do this in Desmos either until yesterday. What's that? This is the second time I'm doing it. I tried it last night and it worked. So a buddy of mine showed me how to do this. So look at what we're going to do. We're going to take rectangles. So I want to see the rectangles. I want to see the rectangles as y goes between 0 and f of 1 plus k over n. Right? That's that rectangle. But on the range where x ranges from 1 plus k minus 1 over n up to 1 plus k over n. Okay, let's look at this. What this means, oh no, don't go back. Okay, obviously I don't know how to use this yet. What this means is for every value of k between 1 and n, let me set n equal to 2 or 4, whatever. Okay, you guys see what it's doing? For every value of k between 1 and 4, what it's going to do is graph a little rectangle. where y goes from the x-axis up to the value of the function at 1 plus k over n, but only in the restricted range where x ranges between 1 plus k minus 1 over n up to 1 plus, I'm afraid to do something, 1 plus k over n. So on each of those little rectangles, we get these values. We get these rectangles. So this is our upper bound. If I used k minus 1 here instead of k, we'd get the lower bound. Okay. Now, Desmos does know the integral. So I don't think I'm giving too much away by saying this, these areas that we're computing are integrals. And look at what the value is, 3 1/3. You guys see that? But we can also look at what the actual approximation is. So the actual approximation is a sum, as we can't use n, let's use j, as j goes from 1 to capital N. The width of each rectangle is 1 over n. That was this width, 1 over n, 1 over n. And the height of each rectangle was f of, should we do the upper, let's do the upper sums, 1 plus k over n. So this is a 4-element list. Not k, j. J is the summation. So here's the upper bound when n equals equal to 4, 3.7. The true value is 3 1/3. But if I start increasing n, so now we're at 3.4. We've got 13 little rectangles below the area. And as we go out to 50 rectangles, now I'm at 3.36. As I go out to 100 rectangles, now I'm at 3.34. And as I keep doing that forever, I'm going to get closer and closer to the true value of the area. Or if I look at the same thing but from below is, instead of taking j, I'll take j minus 1. That's the value from below. In fact, what I was graphing was from below. I'm graphing the rectangles from below, and the rectangles from below start only at 3. And as I increase n, I'm moving my way up to 3.33 as I get farther and farther up. Does that make sense? Yeah. You can do limits. That's literally what this thing is. Yeah. So it figured out the limit. Okay. Does that make sense? Make sense what's going on? Peter, I lost you.
I'm just shocked how Desmos did it.
Desmos is pretty cool. Pretty freaking cool. How did I do it? I just typed int. int. sum. Not su comma, sum. Okay. Peter. Awesome. In Desmos? Yeah, great. So now we're up to the main concept that we're covering in chapter 5. So given any function, what do we do in general? Given any function, nice function, of course, continuous or something, piecewise continuous, whatever, function f of x on a range a to b, we want to find, we want the area, and I'll put area in quotes because if my function does this area is negative. This is negative area. This is positive area. Okay, here's x equals a, and here's x equals b. We want the area, well, I guess area under, maybe under is the thing that needs scare quotes, not area. We want the area under the curve y equals f of x from a to b. And so what do we do? We're going to break up this interval a to b into, so break the interval ab into capital N pieces. You don't have to break it equally. we saw when we looked at what Fermat did, that he didn't break them equally, but for all of our applications, let's just break it equally. So what's the width of each piece? So we're going to break it into n equal pieces. So n equal pieces of width. Yes, the total length is b minus a. So the total length is b minus a. And so if we're going to break each, we're going to break that total amount into n equal pieces. Each piece has length b minus a over. Yeah. That's the width of each of my little rectangles. So here's some little rectangle. And now the height, well, I don't care. You want to take the left one, or you want to take the right one, or you want to take the middle? You want to take the middle, the midpoint, or the right point, you know, or take the point where the function is largest, or take the point where the function is smallest, or take a trapezoid. There's all kinds of variations on this thing. None of them, for continuous functions, they all give you the same answer. So let's just take, for simplicity, let's take the right endpoint. Okay, that's the width of every piece. The height of the kth rectangle. So here's the first rectangle, the second rectangle, the third rectangle, the fourth rectangle. So let's work out the height of the fourth rectangle. What is this point? It's f of something. I start at a, and I shift over by a width of b minus a over n, but how many times do I do that shift? So this is when k is 1, this is when k is 2, this is when k is 3, and this is when k is 4. Okay, so the height of each of those rectangles, we're going to make a rectangle like this. The height of the kth rectangle is the value of the function at a shifted over by the width of each rectangle times k. This is exactly the Riemann sum. That's exactly what we're coming up to. So the Riemann sum, let's, you know, of order n or something. The Riemann sum, do we have a name for this? S sub f of n, something like this? It doesn't matter. We don't need notation for this thing. Will be the sum of all of these areas. So it's the sum as k goes from 1 to n. Every width is b minus a over n, b minus a over n. Every height is, well, the heights are all different, but the heights are f of a plus k times b minus a over n. So that's the sum when you take n terms. And the definition, the integral, so definition, the integral of f from that's an f, that's a f for from a to b is this area, It's written like this, integral from a to b, f of x. You see, this is f at some value. This is how much x is changing. So this is the difference in x. We would write this difference in x. So f of x is each height, dx is each width. So this is height of each rectangle. This is the width of each rectangle, dx. And that is the limit as n goes to infinity of these sums, of these sf of n's. And in fact, that's what the integral sign is. It's just a stretched out s. That's all it ever was supposed to be. Okay, so these finite sums, so the yoga is that finite sums from sigma notation, this is a Greek s, converge as n goes to infinity to an English s. Okay, which is the integral. So this means the area, so we could have written all those previous areas as, so this area from above is the integral of 1 plus x squared. Now I really do need parentheses, because I'm going to multiply it by dx. It doesn't have meaning. People do this all the time. They write 1 plus x squared dx. This doesn't actually have meaning because PEMDAS says only x squared is being multiplied by dx, and then there's a 1 there that's just floating. But people write this all the time. But I always like to put parentheses to make sure this is a height, this is a width. I'm integrating from 1 to 2. Okay, and you can do this for any function. You want to see another function? I mean, as long as we have it all set up. Give me another function, crazy, whatever you want. Sine plus sine of 3 pi x. As a is negative 4.8 and b is 5.2. Oh, this formula has to change because it's not starting at 1, it's starting at a. And we're not multiplying by 1 over n, we're multiplying by b minus a over n. So let me put it like this: b minus a over n times k. And what's the range where that happens? It happens as x goes from a to k minus 1 times b minus a over n up to, don't look yet, a times b minus a over n. Okay, and I think that is literally what we wanted. So this is when a is negative 4.8 over here, and a is 5.2 over here. And this is just the left endpoints, which sometimes are under the curve, sometimes they're above the curve. So it's neither an over or underestimate. And the integral of the function, the total area under this curve is 97.7. And the partial sums, so let's get this right. This isn't 1 over n because the width isn't 1 over n anymore. The width is b over a, b minus a over n. And the function values start at a, skip by b minus a over n's. And well, 98, so this is an overestimate, but there's no way to tell that it's an overestimate or underestimate because, but now we start increasing the value of n, and you see how we get more and more rectangles, and we get closer and closer to the true value of the integral. That's the Riemann integral. That's Riemann sums converging to the Riemann integral. Cool? Does this make sense? All right, let's do one more example. Let's do a couple more examples. I need to give you a quiz at some point. All right, let's do one more example, and then we'll get a quiz in. Example. Let's find the integral of x cubed dx as x goes from 0. Let's make the bottom endpoint 0 and the top endpoint 4. Let's make it b. Let's make it be some number, b. Let's see if we can figure out what this is. So again, we have the curve y equals x cubed. Here's y equals x cubed. We're going to go from 0 to some value b. And we want to know the area under this curve. And we're going to work this out from the definition of a Riemann integral. So we're going to take these Riemann sums. So this is the limit. This is the limit as n goes to infinity of the Riemann sum, Sn. So we have to work out what Sn is. It's going to be a sum as j or k, whatever we want to call these dummy variables. Let's say k goes from 1 to n. So we're going to have a bunch of rectangles. What is the width of each rectangle? B over n. Yeah, b minus 0 over n. Does that make sense? What is the height of each rectangle? Yeah, so where is the location of the kth x value? So the kth endpoint is, it's always a plus k times what we skip by. But in our case, a is 0. So it's just k times b over n. K times b over n. Does everybody see that? Because a for us is 0. So a is equal to 0. So far, so good. And what's the height? So the width of the rectangle is this. The height of the rectangle is that thing cubed, exactly. K times b over n cubed. So far, so good. Okay. So I have a sum as k goes from 1 to n, from 1 to n. I have a b over n times a b cubed over n cubed. That is a constant as far as k is concerned. Those are things that are not changing with k. Ask me, please, because I guarantee you there are 10 other people that are confused about exactly the thing that you just got clarification of.
So where did you get the view? It's just like n is the number of.
N is the number of rectangles. The total length is b because we started at 0. So each rectangle has width b over n. Thank you for clarifying that. I guarantee. How many people? Nah, I'm not going to ask. How many people were confused but were too chicken to say something? Thank you, Nimmer. Thank you for being honest. If you're confused about something, there are 20 other people in this room that are also confused about that same thing. Please ask. Nimmer, did I lose you? Now you're good. You promise. Cross your heart and hope to whatever. Okay. B over n. Then there's a b cubed over n cubed. B, so what is that? B to the 4th over n to the 4th. So I get a b to the 4th over n to the 4th out front. And then I have a sum. All that's left over is k cubed. If only we had a formula for the sum of the first n cubes. You remember what it is? Yeah, it's the square of the sum of the integers. So let me get this b to the 4 over n to the 4 down. And then what's here? N times n plus 1 over 2. But everybody's going to get squared. So n squared plus 1 over 4. Everybody see that? So what happens to that as n goes to infinity? As n goes to infinity, these Riemann sums converge to a limit, and that limit is, yeah, there's an n to the 4 on bottom and an n to the 4 on top with a constant factor of b to the 4 over 4. And that's all that matters. So the answer is b to the 4 over 4. Let me remind you that that is the integral from 0 to b of x cubed dx. And hopefully you're starting to smell something that smells like a antiderivative. Same. Okay, so I'm looking at this quantity for any value of n, and I'm going to make n larger and larger. So what this is just a polynomial in n. The leading term here is n to the 4. The leading term here is n to the 4. So n to the 4 over n to the 4 goes to 1. Nothing else matters. These lower order terms don't contribute anything in the limit. And then there's a constant of b to the 4 over 4 at front of everything. Okay, cool. You guys just computed your first Riemann integrals. Bye. Say it a little bit louder. For rigorous sigma notation. Yes. Okay. Very good question. Very good question. The question was, if you wrote here a sum as k goes from 1 to infinity, would that be wrong? Right? That's your question. It would be wrong. Why? If I add up the cubes all the way out to infinity, that's infinite. Now, what you really mean is you have to keep track of the fact that this is also n. So you need something like b to the 4 over infinity to the 4. Now you start to see why you don't want to write things like this, right? You want to leave it some finite number n. Once you've worked everything out, then you take the limit as n goes to infinity. Does that make sense? Hari. I'm going deaf. A little louder. Yes, exactly. On an exam, I might say, compute this integral using from the definition of an integral. This is what that means. Okay, in the same way that I would ask you to compute the derivative from the definition of derivative, meaning a limit of f of x plus h over yada yada, right? That's the definition of derivative. Of course, we don't compute derivatives that way anymore now that we know lots of rules, unless we're asked to. In the same way, we're going to learn lots of shortcuts for computing integrals so that we don't have to do this annoying thing every single time. But for now, that's all we know. Okay, that's coming next time. That's the fundamental theorem of calculus that will let us, I mean, I disagree with the choice in the book to introduce this symbol as the antiderivative before we understand anything about why that is the case. But in fact, that's exactly where it's sort of, I can see, I can go either way. So we're going to learn something called the fundamental theorem, probably next lecture, that will allow us to compute these integrals much more efficiently than going through this kind of thing every single time. And in the same way that, you know how we had these derivative looking limits? And unless you know the shortcuts for why that is a derivative, and you can compute those easily, you wouldn't be able to compute that limit easily. In the same way, you can set up things that look like limits, but you don't know what that limit is unless you recognize it as a Riemann sum. Does that make sense? So just to give you an example of that, should I give you an example of that? Okay, here's an example of that. Here's an example. Recognize, so here's your problem. Recognize this limit without computing it. Without computing it. Okay, so here's the limit I want you to recognize. 3 minus 7 over n. So this is a limit as n goes to infinity. 3, let's make it 3 minus -7. -7 over n times a sum as k goes from 1 to n of, oh gosh, e to the 3 plus k times 10 over n. I don't know. So yeah, that. What the hell is that? How do you make sense of this? Okay, scratch your head. What's going on? Does it look like something that we know? Remember what the Riemann sum is. The Riemann sum for any function, the Riemann sum, the finite sum for any function, this S of n, is a sum as k goes from 1 to n. B minus a over n is the width, and the height is f of a plus k times b minus a over n. Right? That's the height of the kth rectangle. The widths are all the same, b minus a. Can you try to guess what b should be in this case? 3. What should a be in this case? -7. And what should f of x be in this case? E to the x. The distance between 3 and -7 is 10. And this is just a plus this thing. So this is the function e to the x. So this limit will be, so recognize the limit without computing. We don't know how to compute these things yet, but it will be the integral from -7 to 3 of e to the x dx, whatever that is. So what does this limit represent geometrically? You take the function e to the x. Here's the function e to the x. Here's -7. Here's 3. It's this area. That's what this god-awful limit is. Does that make sense? Question? Oh, you're absolutely right. So excellent, outstanding. This should be a -7 and not a 3. So in order to make this a -7 and not a 3, I have to multiply. So if I want this, let's leave the problem exactly as is, because that's an even better problem than the one I came up with. This should have been a -7, which means it's off by a factor of e to the 10. So if I multiply by e to the minus 10 and I multiply by e to the plus 10, I don't do anything. E to the minus 10 makes this a -7, which is literally the integral that it should have been. And then e to the 10, so it's e to the 10 times this amount. Okay, that's a great problem. I got to remember that. How to hide the fact that the starting value should have been -7, but I put the wrong thing in. Awesome. Okay, everybody see that? What's that? That's nasty. That's a little mean. That's a mean problem.
How does negative ten make that?
Yeah, here was an e to the 3, and it should have been an e to the -7. So if I multiply by e to the -10, that'll make that an e to the -7. But I can't just multiply by e to the -10 willy-nilly. I have to multiply by e. If I'm multiplying by e to the -10, I also have to multiply by e to the plus 10. So that doesn't change. So in fact, this is e to the 10 times that area. That's a great. Oh, I gotta remember that. We're writing the final exam, so we need some juicy problems. All right, let's do one more. Let's make this the quiz. Okay, so here's your quiz problem. Hopefully I won't get this one wrong. Recognize, let's call this recognize the limit as n goes to infinity of the sum. Oh, by the way, this was outside of the sum. Does that matter? This is a constant. Doesn't as far as k is concerned, doesn't depend on k. So this can go inside or outside the sum, whatever you prefer. I like to leave it like this so that it's clearly width times height, but just as well it could have been outside. Okay, so let's recognize a limit as k goes from 1 to n. Don't look. I got it. As k go, oh, there it is. As k goes from 1 to n, I'm so predictable with my numbers. 6 minus 3 over n times tan of 2 pi over 3 plus 3k over n plus 3 plus 3k over n to the 5th. Okay, it's just some stupid thing. A sum is k, so the limit as n goes to infinity of the sum as k goes from 1 to n of 6 minus 3 over n times tan of 2 pi over 3 plus 3k over n plus 3 plus 3k over n to the 5th. Actually, this kind of gives it away. It's not good if I do it like that. It gives it away too much. Okay, just recognize it as what this limit represents geometrically. Okay, so obviously the point is that it's some kind of integral. It's an integral from what to what? Oh, it's a quiz. So think about it for a second. Think about it for a second. Give me a thumbs up when you know what it is. You guys are still working? You know you just look at it. There's nothing really to compute here. You just look at it. Does it look like a Riemann sum? Do I have a b minus a over n and some function of a plus k times a plus, okay, whatever. I can't say it out loud. The length, yeah, Jenny. You want to ask what it is? Yes, so let's see. Did you get that the lower bound was 3 and the upper bound was 6? Because the width of that is 3, so that's what this 3 is doing. And then what's the function? It's tan of 2 pi over x, right? Because I'm doing tan of 2 pi over, this is the kth term, plus, what is this? K to the 5th, x to the 5th. all of that times dx. And I would prefer if you put parentheses here every time, although many people don't. Okay, here you don't have to put parentheses. It's clear the tan is only of this thing. So that's it. So if you got the lower bound 3 and the upper bound 6, give yourself a point for each of those. If you figured out that what the pattern is of the function, give yourself another point, and it's worth 3 points. Pass them down, please, and then we'll take them up.